היי מיכאל.
היי.
אני שנייה חוזר, בסדר?
אין בעיה.
רגע. מה את אומרת? וואי, זה קיוטי.
אם היית
למעלה יש.
שבת, זה סביר לאספרסו, לא?
מה? זה סביר. לא, אני גם מתעסקיר, כי אני כמה נקראים, זה מין עכשיו.
מה יקרה?
לא, זה לי שם עושים כבר, למה?
כן, אין הסרטים
בדיוק, מה שיקרה, זה ממש בגן שונה. היום האחרון, בסוף הגיל שלה, נמצאות של אורן. היה ממש כמובן. נמצאות של אורן. ואז הוא יצטרך, כן, של אורן. וזה בין איכשהו נמצאו את העניין בחוק. גם כולם ביחד.
כאילו, אני איכשהו כמה זה לא קרה לנו, לא היה לנו דיונים מעניינים איכשהו, אבל באמת.
וואי, זה ככה, זה כאילו, זה לא ככה מדמיין. ריפלים קטנים. זה קורה לי, אני יודעת. תאמיני לאן. כן לנו בעיה אותו דבר. וגם כל ספוזיטיב שלו הוא לא הבעיה. תאמיני מי שעושה פוזיטיב, כנראה שהוא חולה. מי שעושה נגטיב, יש סיכוי עדיין שהוא חולה. טוב, ביי. היי חבר'ה.
היי, מה המצב?
בסדר, how are you doing? היי הנה. Jonathan, Yaari, another Jonathan.
Hi.
Good to see you. Let me share the link of the Jamboard in the chat. What's the problem? Wait a second. Oh. So I think you have a Jumbo link. I will also share a screen, but for those of you who prefer to have the ability to go back and forth, it might be useful. Share screen. Okay. So, I'm just turning off all interruptions. Okay. Yes, I think it's fine. Okay, so I remind you that last time we discussed about the injective envelope of an operator system. And we said that any operator system admits a unique injective envelope, which is a sister algebra. If the operator system sits inside B of H, then we can verify that the injective envelope also sits inside B of H as a sub-operator system, not as a sub-sister algebra, and it contains S. And I asked you to read at home a little bit about some relating properties. So let me just briefly discuss about them. So some related properties. Right, so there's the notion of essentiality. And we say that E is an essential extension of S if whenever I have in fact it's a categorical property, but okay, I'm just describing it now in our category. If whenever I have just an embedding of S into some T, and somehow we have an extension of it, or another way to think about it, suppose you have a map, a UCP map phi, and its restriction somehow is embedding, then the extension is called essential if phi has to be, if whenever we have such a situation, phi has to be embedding as well. So units are completely isometric. Okay. And there's the notion of rigidity. What is the rigid extension? Rigidity. I say that E is a rigid extension if whenever I have a UCP map E, such that whenever I restrict it to S, I get the identity map on S. So if whenever I'm in this situation, it must be the case that phi is the identity on E, then we call this extension a rigid extension. And I gave you as an exercise to verify that minimal injective extension is equivalent to being maximal essential or maximal rigid, or essential and injective, or rigid and injective. So all of these 5 options are equivalent. Okay? Okay. So now, please interrupt me if you have any questions at any point. I mean, feel free to interrupt. Okay. So now we turn to G-operator system, which is a new category. So what are G-operator systems? And this begins some of the third part of our course. So always for us, G will be a discrete group. G will be a discrete group. I will never consider, although in some cases I can, but I don't want to do it. I want to be consistent, and I'll consider only discrete groups. And you know, and we call X. So if a compact Hausdorff space X is called the G space if I have a homomorphism of groups from G into the homeomorphisms of X, mapping well, I don't know, maybe homomorphisms already includes the property that E goes to the identity, but if not, then let's say it is the one of the group, okay, so this is something you're probably familiar with, this way or the other, and we denote it like this. And G operator system, or an operator system, S is a G operator system if there is an homomorphism, sorry, from G to the automorphisms of S. By saying the automorphisms of S, I mean the automorphisms in our category, namely UCIS isomorphisms. So these are just UCIS isomorphisms. And mapping again E to the identity. And okay, and usually, okay, you know, maybe sometimes I can give names to the actions, but if there is only one fixed action, then usually I will just denote it. So okay, so both in the operators, in the space cases and in the system cases, sometimes, I mean, I can give the action the name alpha and then write things like alpha, I don't know, G of X. So this would be some Y, right? X is, and sometimes, I mean, if we know who is alpha, then I would just write G times X or something like this. Okay. And okay, and these are so first example for an G operator system would be what? So of course, if I have an action on some X, I can turn it into an action on C of X, right? Just by precomposing with the homomorphism. So this is a sister algebra. In particular, it is an operator system. And just a reminder, last time we said that whenever we have an isomorphisms of sister algebras in the category of operator systems, so whenever I have two sister algebras, A and B, and I have an isomorphism between them, that is isomorphism of operator systems, so it's just the UCIS isomorphism, the unital completely isometric isomorphism, then automatically they are isomorphic as sister algebras. So this map is multiplicative, the isomorphism. So I'm just saying that if I give you as an example of a G operator system a G sister algebra, then I mean, a priori you should say, but Guy, the action is not via the right automorphisms of sister algebras. The action is via the automorphisms of operator systems by your definition. But it doesn't matter. This is what I'm saying. So if you have an action on a sister algebra as an operator system, it is also an action as a sister algebra by what we said last time. Okay, so just a remark. If A is a sister algebra, is a unital sister algebra, and G acts on A as an operator system, then by the lemma we showed last time, G acts on A via star isomorphisms. So we can feel we can call it a GC star algebra, and we don't need to distinguish it as a different category somehow. It has the same. Okay, the same. Yes. So what about the maps? What about the morphisms? We discussed about the object. I'm moving to page 2. The morphisms will be a linear map. A linear map. But by the way, let me just say another thing about the previous page. I said here that whenever G acts on X, then G acts on C of X as a G operator system or as a C-star algebra, but also vice versa, of course. You know, whenever you have an abelian commutative, an abelian unital C-star algebra, and I have an isomorphism, an automorphism of it, then it translates to an automorphism of the Gelfand spectrum. So it goes in both ways. Okay, so back to the morphisms. A linear map phi from two G operator systems between two G operator systems is G equivariant if phi of Tx is T of phi x for every T in G and for every X in S. And note that there are two different actions here. This is the action of T and this is the action of S, of course. And we will consider if phi is also UCP, we'll call it GUCP. Similarly, we'll have, I don't know, GUCCs, GUCs, etc. G star homomorphisms. Okay. Okay, now a remark. If I have an operator system, a G operator system, then, well, even before saying it is a G operator system, if it is just an operator system, I can always construct a G operator system out of it. How? I can consider the following space. I can consider L infinity of G comma S. So what is this space? It is, think about it as a space of sequences indexed by the group elements G with values in S. Okay, so this is just a sequence space of over G with values in S. You can of course you can put it. Okay, you know, I can take this A to be B of H. So I can put this inside L infinity of G of B of H, and this sits of course as the diagonal of B of L2 of G with H values. So this is an operator system. So L infinity of GS is an operator system. But I can also act on it. I can do something like this. I can define T times F at a point X to be F of T inverse of X. The reason I put inverse is that it will be an action. So it will be a normomorphism. So T times H times T times S times F will be T times S times F, etc. So so for every T in G and X in S. And okay, so this is
Guy?
then.
Can you explain the last equality? Why is L infinity G with values in BH the whole bounded operators on L2GH?
No, it is of course a mistake. I just meant to write something like this. These are the diagonals.
Yes. Yes. Thanks.
Thanks. So we can always tone in an artificial way somehow, right? I mean, so no. So sorry. So I mixed up. Here I just say that this is an operator system. Now I'm just saying that if G right so I need here to define this. I needed to have an action on if S is G operator system, then we can define this. So L infinity of G of S will be right. I used here the action of G on S, of course. Okay, and now I want you to note that and this.
Where did you use the action of S of G on S?
Here.
Isn't that acting on G? Shouldn't that act on G?
What? I mean, F
takes values in G. No, how can?
No, it takes values.
No, you're right. You're right. Sorry, I mixed up between two things. Sorry. Okay, let me just rearrange this. You're right. No, I wanted to say two things and I confused myself somehow. One thing I wanted to say is that I can tone it even without being a G operator system. I can construct the following thing. Thank you. Sorry for that. Yes. So this is always with this action, this is just a G operator. This is a G operator system. Now another thing I wanted to say. If S happens to be a G operator system, if S is a G operator system, we always have the following embedding. We always have iota from S into L infinity of G of S, sending X into, well, the only thing it can be, right? Iota, let's call it iota. So iota of X at the point T will be T inverse times X. Then where was it? Then iota is G of C. This is what I wanted to say. Is G. Okay, so sorry for the confusion. There are two things. One, whenever I have an operator system, I can construct out of it an artificial G operator system, L infinity of G of S. This is one thing I wanted to say. Another thing I wanted to say is that whenever we have a G operator system S, we can in fact think about it as sitting in this guy. Good.
Guy?
Yes.
So L infinity of G of S is just bounded functions, and the coordinates are from G, right? We have G coordinates and the values are from S, right?
That's right.
So the function F, the input is not elements in G.
That's the function. And T is in T here is in G.
No, I'm talking about the first remark. T of Fs.
So S is in G. You're saying there is, yes, sorry. I mean, it's a part of the previous mistake. S is also in G.
Okay. Thanks.
Okay. So now, okay, suppose that S happens to be somehow injective. Suppose that S happens to be injective in operator systems with UCP maps. Then I claim that L infinity of G, comma S is injective in GEOP systems with GUCP. How come? So in short, we will call it G-injective. We'll call it G-injective. How come? Well, you just need to follow the arrows, right? So whenever, okay, suppose I know that S happens to be injective operator system, and I have now I want to show that L infinity of G of S, right? I want to show that this is injective. So I need to show that whenever I have T sitting inside some R, both of them are G operator systems. So this is a job, right? This is just a GUCs. And I have a GUCP map into here. How can I right? So on the one hand, we have a map to S, right? I mean, here we have the evaluation in 0 in E, in the trivial element that goes to S. Therefore, by the usual injectivity, we get here a UCP map. But now we know how to push S in a G equivalent way into L infinity of G of S, right? So this will show, and this will make everything G equivalent. So this will show that this is G injective. So okay, verify the details. I mean, there's nothing here to do. Just checking that everything works and everything works. So example, L infinity of G of B of H is G injective. Why? Well, Alverson's extension theorem tells us that B of H is injective, and what we just said tells us that it is G injective. By the way, just a reminder, we also showed last time this guy is also injective. Reminder, we also showed last time L infinity of G, comma B of H is injective. Questions so far? Something was too fast? or too slow? Or unclear?
How did we see it? Maybe.
Yes, so the idea was like this. Recall that we have this containment, and it's really easy to throw a UCP projection from here to here. How come? I mean, it's the diagonal. Just compress everything to the diagonal nicely. And so if this guy is a GUCP projection of this one, then we know it is injective. Now I claim that this fact, this example shows, in fact, it tells us that every G-injective operator system is automatically injective. So corollary from what? There wasn't a claim, but still it is a corollary. Corollary, I'm now in page 3. S is G-injective as a G-operator system. As a G-operator system implies S is injective. Proof? So I can put S right inside L infinity of G comma S, which sits inside L infinity of G comma B of H. And by, sorry, by G injectivity, קיים GUCP projection. Right? We always know that whenever something big is injective and something small is injective, then there is a projection. Now it is GUCP projection because everything is G injective from the big one to the small one. But we also have, right? We also, I mean, this is also injective, but L infinity of G of B of H is also just injective, is also injective. So S is also injective. I remind you that being injective is equivalent to being a juice, to being a projection of somebody else that is injective. But this was categorical, so it doesn't matter if we have G or not. So by assumption, I have this map, but now forget it is a G map. It is also just also UCP projection. Therefore, S is injective. Okay? Okay, so corollary, from the corollary, if S is G injective, then S is a sister algebra, right? Because it is injective, and we know that injective operator systems are sister algebras. But recall, it is a G operator system, so the action is by G UC automorphisms, but therefore the action is also by star isomorphisms. So it is in fact, I mean, I can erase here sister algebras, or just adding hence S is a G sister algebra. Right action by star isomorphisms.
So you also have a G action on the spectrum, on the Gelfand spectrum?
If it is commutative, but it doesn't have to be commutative.
Okay.
But that's the point. If it is commutative, it means that you have a G space, that you have an honest to God G space. Good. So, so theorem of Amana. So this theorem came Benny, you said you'll bring Rashan. So this theorem came maybe 6 years after, yes, I think this paper was from 85, and the theorem that we studied last time was from 79, so 6 years after the previous one. And it says, it says the same thing. It says that in the category of G operator systems, with G UCPs, every S in B of H, G operator system, admits a unique up to what? Well, I will write and you will understand it, up to a unique S preserving G uses isomorphism, injective envelope, which I'll denote by I subscript G of S, and I can put it inside an infinity of G comma B of H. We call it the G injective envelope of S. Proof. So I'm just going to tell you it is the same proof as in the trivial case, in the case where G is trivial, in fact, G operator systems and UCP, only with L infinity of G comma B of H in the role of B of H. So I will skip the details because it is just the same proof. You go over all the proof, you construct these semi-norms and these from last time that corresponds to what we called S-map. We just write the same proof, but with G equivalent maps, and it all works out. The only thing we need is we need to have some kind of injective roof above us, and in the previous proof, the roof was B of H due to Alverson's extension theorem. And now the roof is L infinity of G comma B of H, which is due to what we've just said. Okay, so it is the same proof. So and also another remark, all equivalences mentioned in question 6 of homework 2, these are the equivalences I mentioned at the beginning of our meeting today, they also hold for in the G equivalent case, also hold G in this category. Okay, so your maximal G essential. So right, if and only if you're minimal G injective, etc., etc. Okay. Another remark I would like to make is the following one. We know, I remind you that by rigidity, we know that the automorphisms of S sits inside the automorphisms of Yoda, of the usual injective envelope of S. How come? Because whenever I have an automorphism of S, there is only one way that I can extend it to an automorphism of I of S. So this tells us, in fact, that I of S is also G operator system, because I can extend all the actions. Whenever you have alpha t, I can extend it to alpha t twiddle on all of I of s. So for each g, so for each t and g, alpha t, so alpha t is now the action. Now I do denote it by something, extends to alpha t, I don't know, twiddle in automorphisms of I of s. Okay, so I of s, the usual injective envelope, is also G operator system. And it is a G operator system, and it is of course a G extension of S. So that's the picture you should have in mind. I have S, it sits inside I of S as a G suboperator system. So okay, I can in fact I can truly embed it here, we know it. On the other end, I also have a G uses from S into the G injective envelope of S. Because of G injectivity, I can add a map here, right? So קיים GUCP since IG of S is G injective. But what can we say about this guy? But since I of S is essential, I'm not using G essentiality, I'm just using usual essentiality, this GUCP map needs to be uses, right? So let me go back 2 pages. What does it mean to be G essential? To be G essential, it means that whenever you sit here and there is a UCP map to somewhere else, and the restriction to the guy that you are essential extension of is uses, then you yourself are uses. Units are completely isometric. So that's the case that we now have. So by essentiality of this guy, this map is in fact uses. So but since iOS is essential, the red map is uses, and it is also a Gmap because it was a Gmap before. So we're in the situation that S sits inside I of S, and this sits inside the G injective envelope of S. And all as G operator systems. As G operator systems. I mean, each guy is a sub, you can think of it as a sub G operator system of the guy that sits above it. Okay.
So I of S is not G injective, that's the point?
Exactly. I of S is not G injective. It is a G injective operator system that is not G injective. It does not have this property. Well, I can always extend the GUCP maps that comes from S and to extend them to T into a UCP map because I of S is injective. But this extension will not be in general G equivariant. I cannot promise it unless somehow they coincide. But usually they will not coincide, you will see it, even in the very simple cases. Of course, if the group is trivial or something like this, they do coincide. Okay. Questions so far about these issues? Okay, if not, then I want to have a small pause with these guys and to discuss just to say a few words about amenable groups. So let me ask you, do you all know what an amenable group is? Is there anybody who doesn't know what an amenable group is? Do you know? So okay, I want to use the following definition. I want to say that an amenable group is defined if there is what is called an invariant mean, a positive unital function from an infinity of G onto the complex number. Okay, you can take R, but we are going to take the complex numbers, of course. That's why it will stay in the category we want. And I will also want to use the Fellner sequence equivalent definition. So are you all familiar with the Fellner? I will remind them, but I just want to know if it's the first time you're going to see it or the second. Okay, so let me just briefly spend the next 3 minutes about reminding things. So definition. G is called amenable. G is called amenable if there is G invariant unital positive linear map phi from L infinity of G onto C. And it's also known as invariant mean. That's the terminology. Amenable, it has a mean somehow. And think about this map phi as UCP, right? I remind you that unital completely positive map positive maps are automatically completely positive. Definition. So now I want to give the second definition. G satisfies the Fellner condition if I can write it as a union, increasing union of sets F1, F2, etc. Finite sets, such that the limit of the הפרש symmetry, the symmetric difference of Fn and Tfn goes to 0 when I divide it by Fn. Or equivalently, if the intersection, so this is for all T and G. Or equivalently, whenever you act on Fn, then you don't change it so much because the intersection of Fn and Tfn is almost everything goes to 1 when you divide it by Fn. And claim G is amenable if and only if G satisfies the Fellner condition. So did you see it at least once in your life, this equivalence? I mean, so if you read about it, try to think about it also in our language. I mean, I think it's nice. I mean, you construct. So what do I mean by that? For example, I don't know. Okay, let me just maybe sketch a proof of this direction, right? So right, so you can say something like phi n, which is let's define, right? You can define phi n of f to be 1 over Fn times f of t T and Fn are UCPs, then you can automatically use the BW topology we have on UCPs, right? When we know UCPs from L infinity of G to C is compact, so we can find write some F and K subsequence that converging to F, and then it's easy to show that this phi needs to be invariant. The other direction is, of course, the more complicated one, but also you can try to think about it in our language. So think about this direction too. Okay. And just, I don't know. Okay, and you know examples of, you know that every abelian group is amenable, every, so in Z you can of course construct, you can of course take the Fellner sets to B minus NN. It's really easy to show that it is Fellner set in general. Every abelian, or even nilpotent, or even solvable, will be amenable. Okay. And an example of a non-amenable group?
F2.
F2. Okay. So now let's go back to operator systems, to the G-injective envelope. So back to G-injective envelopes, back to the G-injective envelope. We didn't see any example, right? Let's try to figure out what is the simplest example in the world. So the simplest example. So what is the simplest example? Who is going to be S? Well, it must contain the unit, so it must contain all the complex numbers. But the simplest case in the world is if S is just the complex numbers. And the G action is just the trivial one. Okay, do nothing. So what is the G-injective envelope of S, of C? So, of course, the first guess should be probably it's C, right? It can be interesting somehow. But look, if, note, if IGC is equal to C, then it means what? We know that we have, so okay, let's go back just one slide. I'm going back to page 3. Hamana's theorem tells us that IG of C will sit in L infinity of G, right? So L infinity of G is injective. So by the G injectivity of the injective envelope of C, we know that there is, I mean, regardless if, no, I just want to say the following thing. Note, we know that there is a GUCP projection from L infinity of G onto IG of C that sits inside L infinity of G. Because it is G injective and sits inside L infinity of G. But if it is equal to C, then this will tell us that the group is amenable, because this GUCP projection will be the invariant mean. So if IG of C is C, then G this, then this GCP projection will be an invariant mean. So G is amenable. So we already know that the G-injective envelope of C for G equal the free group is not going to be trivial, right? And also vice versa. And also, if I have a map, if my group is, and also if G is amenable, then there is, I can think of it as a GOCP projection. The invariant mean, I can think of it as a GOCP projection. Right, just identify C as sitting inside L infinity of G. And it is GOCP because everything is commutative. So this tells us that C is G injective. So C is G injective. So it has to be the G injective envelope of itself. Okay, so to sum up, theorem, G is amenable if and only if its G injective envelope is trivial. Okay? I'm going to write it in page 5. So theorem or claim, G is injective if and only if IG of C.
G is amenable, right?
Sorry, amenable. If and only if IG of C is
Does it also mean that it acts trivially? Can it act not trivially on?
Yeah. So
on the spectrum, for example, if it was.
That's correct. So now you're asking whenever G is not amenable, do I know that the action must be non-trivial on the spectrum, on the Nagle-Fan spectrum? The answer is yes. We're going to see it. We're going to see things that are much more stronger than that. Just this observation. Okay. Now recall that. I want to say something that maybe I should have said in this part, but so maybe I should have said it here. Note for a second, these guys are sister algebras, right? But I said that this sits here as a G operator, as a sub-G operator system. I just want to remark that, in fact, it also sits here as a sub-sister algebra. So more generally than that, I want to say, maybe, I don't know if okay, maybe, okay, you know what, I will say it later. I will need it later. I wanted to say something that is more simple, but okay, but observation, IG of C is a sister algebra, but it is an abelian one. How do we know it is a abelian one? Okay, maybe I'm not clear enough. I want to say we know this is a sub-operator system of L infinity of G, right? L infinity of G is in abelian sister algebra. Why is the G-injective envelope of C, which we know is a sister algebra, but I didn't say it is a sub-sister algebra of L infinity of G, right? It has a different product, a different multiplication. Why it is commutative too?
The Choi-Efos construction was like if our construction, no?
from the construction, because we have here these phi, and the product here on elements A and B, A times B is phi AB, right? So if this product is commutative, and it is, then the product, also our product, is commutative. So it is an abelian sister algebra, unital, of course. So therefore, it is C of something. And it is C of something interesting that we now know that might not be trivial. Let's give it a name. So let's call it the Hamana boundary of G, okay? I'm just saying that usually this will not be the name of this object. You can find it only in one paper if you Google it. But let's call it the Hamana. So that's the definition. The Hamana boundary. Hamana boundary of G. This is not the usual name. But for us, it is a suitable name because it came up from the construction of Hamana. I don't worry, I will tell you what is the usual name in a minute. Okay, and it means that there is an action of G on this Hamana boundary, because what we have mentioned. And G acts on the Hamana boundary. So I want to understand this action in general. There are a few things I want to understand. First thing I would like to understand is the stabilizers. This will be important for the later, for next week maybe, when we discuss about sister simplicity. But I mean, it's interesting, I think. It's just interesting also. So okay, what do I want to say about the stabilizers? So claim all stabilizers. So maybe let me just remind what are stabilizers. Then you fix a point X and you look on all the G's, let me call them the T in G, such that Tx is X. Now think about it. Of course, stabilizers are subgroups, right? So I'm just claiming that they are amenable. Okay, I should have said something. All stabilizers X in the Hamana boundaries are amenable. So let's show it. So let X be in the Hamana boundary. Then we have, right, the GUCP from an infinity projection into the Hamana boundary, continuous functions over the Hamana boundary. And we can always take the evaluation at the point X and evaluate a function at the point X. This all map, think about it. Well, what can you say about it? The first part is G invariant. The second part, well, it is not G invariant, but it is at least G sub X invariant. It is invariant under the stabilizer, right? So this map, so F X composed with phi is a G sub X invariant state of an infinity of G. So this almost says that we got that G sub X is amenable. We just need somehow to push L infinity of G sub X to L infinity of G, right? The only missing part is how to put here L infinity Gx in a Gx equivalent way. This will give us the invariant mean on G of X. Now I just want to construct this, and this is something general and very easy that you can always do. So how do you do it? But whenever, so let me just say, whenever H is a subgroup of G, we can construct a star monomorphism from L infinity of H into L infinity of G. So how do you do it? Just somebody tell me in, I mean, it's not natural, this star monomorphism. Somehow I need to choose representatives. So you choose representative for the cosets, for let's say the right cosets, and then I can push F. So okay, maybe just briefly I would say choose representative, system of representative R alpha for the, I don't know, right or left, let's see. I think right, or the right cosets. And right and declare do row of F. So now I need to say what it does to G. Write G in the unique way as some R, as some, I don't know, S, R alpha, where R alpha is in the representative. Right? So and S will be in H. And then define this to be F of S. It's very stupid way, but it works and it does the job. So okay, so think about it.
It works for any choice, or do you need to choose in a correct manner representatives?
For any representative. I mean, there is nothing special going on here. It just works. I mean, just verify it works. Yeah. So okay. So now do it for the stabilizer. So rho. Okay, let me call it rho sub H.
This is not the unique decomposition of G. If we have the
Yes, the unique decomposition. This is what I meant.
okay.
So rho GX composed with phi composed, vice versa. Sub GX composed with phi composed with the evaluation in X from L infinity of G sub X onto C is GX UCD. Okay. Good. We already know one thing that is interesting about this action. Stabilizers are amenable. Claim. So definition. An action is called minimal if if there are no G invariant proper non-trivial closed subsets of X. Or equivalently, if for every X in X, the orbit closure is everything. Do you see why these are equivalents, the two definitions? So of course,
Right?
yes.
A very small technicality, but don't you want things that are constant on left cossets, so that indeed it will be, this rho H will be a H map?
Okay, so there is a chance you're right. I calculated it with
Okay, whatever, but you
and it
want,
did the job, but okay,
right.
check the details.
But you want rho H to be an H map, right?
I
To make sure.
just need rho H to be an H map, yes. So if I did this wrong
Okay.
and it needs to be left, then fix it, please. I mean, you just need to write it and verify. One of the sides does the job, but yeah. Okay. And maybe it's left, yes. Yes, okay, never mind. So I hope you do see that these two definitions are equivalent of being minimal by saying that you have only, so every orbit is dense, or to say that you don't have a proper non-trivial G-invariant closed subsets. Okay. And claim the action on the Amana boundary is minimal. Proof. For every x in the Amana boundary, I can think about the restriction map as going, so the restriction okay, I mean, think about this map. There is a map that goes from C of the Amana boundary into C of Gx of the orbit closure. So this map just takes F and restrict it onto this closed subspace, right? This map preserves the unit. Where should I write it? This map preserves the unit. This is unital. So it is GUCs here. By the G essentiality, the restriction map is also GUCs. But how can a restriction map be isometric? Only if you restrict to yourself, right? In fact, there is something more interesting along these lines. We've just showed that we've just gave another terminology of minimality. I mean, saying minimality is just equivalent to say that you are G essential extension of C, right?
Guy, what did you use the fact that you took the closure of a stabilizer? I mean, for any closed subspace?
Yes. I mean, the definitions are equivalent to say that you just need to be G invariant.
Any G invariant closed subspace. Okay.
Yes, it works for any G invariant closed subspace. I could take, well, in fact, I had two definitions. I could use the first definition. I don't know. I used the second one, but I mean, they are equivalent, of course. Okay.
Okay.
Maybe it's a good point to take a break. And okay, so let's take I don't know how much time do you want? 15 minutes? Okay, so 15 minutes break.
So
Okay. Everybody, are you around? Jonathan, Michael, Benny, just make a sign that I will know that Michael, yes, there are two Michaels. Yari, I know that he's here because he was in my room until 20 seconds ago. Okay, Jonathan, are you here? Benny made a sign. Jonathan? Let's wait another half a minute or so. Maybe in the meantime, I will tell you where wait a second, I have a problem here. Okay. So we showed the G minimality. And I see that Jonathan is now back. Okay. So we're good to go. So just a quick lemma, and then I will go to the next property, and I will use this lemma later. So a quick lemma. For every probability measure on the Amana boundary of the group G, I can define the map P nu that goes from the G injective envelope of C into an infinity of G and maps F into the function P nu of F, that what it does to G is G times nu of F, or usually I call them T, right? So let me call it T. What is T times nu? T times nu, maybe I should. So if G acts on G on X, G also acts on prob X by T mu of a set A. A measurable set is mu of T inverse of A. Okay, so what's the lemma? I didn't say anything. I just said consider this map. It is sometimes called the Poisson map. Then it is isometric. Proof follows by what? Essentiality.
Essentiality.
Right. By G, essentiality. Right, restricted to the complex numbers, then it sends 1 to 1, so it is unital completely isometric, so it has to be unital completely isometric on everything. Okay. Definition. So I will use this lemma in a few minutes, but I just wanted to say it. An action is called proximal if for every x and y, I don't know why did I say different, I can say for every x and y, I can find a net in G such that the limit of T alpha of x is equal to the limit of T alpha of y. So I can push 2 points by applying a net into a joint point. Such actions are called proximal. Example. So are you all familiar with so you know that the free group acts on the so-called, sometimes it is called the Gromov boundary of the group. Maybe let me describe it easily as one-sided infinite words, reduced words. So if F2 is generated by A and B, then in A, B, A inverse, B inverse. So it is also the space of geodesic rays on the Cayley graph, if you want. This is so-called, this is sometimes called, also known as the Gromov boundary. So I'm claiming that this, I'm acting by concatenating. I'm acting the action is from the left by concatenating. Also, I didn't define a topology. Concatenating in a how do I write this? Concatenating from the left. The action is by concatenating from the left. And the topology given by a metric. So I say that say that the distance between two words is the 1 over the first let me call it W.
You can take the graph distance in the Cayley graph.
Yes, I know, but I don't. Can I say Cayley graph in this course? I don't know.
I think it's okay.
I think it's okay. So yes, it's the distance in the Cayley graph. Or I mean, it's easier. I mean, it's more. So if you write W as W1, give me another letter. Okay, let me call them X and Y. X and Y. If I write X as X1, X2, X3, blah, 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 and Y as Y1, Y2, Y3, blah, 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 then it's the first 1 over the first, the minimal I, such that Xi is not Yi, where I wrote this in reduced form. Yes, this is also the distance that Jonathan has mentioned, and I think I'm done. So this is the action is proximal. Why is the action proximal? Because obviously I can choose my favorite word, which is of course AB, 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 AB. I don't know why. And then start concatenating the right characters from the left. Well, I might have a problem if I started from, if X or Y were BA, 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 or B inverse A inverse B inverse A inverse, or something like this. Okay, so maybe I can choose another word if that's the case. I mean, but it is proximal somehow. So okay, so think about it. Can push any two words, any two infinite words into a fixed one. Okay. Another definition, the action of G on X is called strongly proximal if the action of G on prob of X is proximal. Now, the action on prob of X is affine, so it preserves extreme points, so it preserves the action on X. So it means that that X will always be G invariant in probe of X. So therefore, strongly proximal implies proximality. Note that strong proximality implies proximality. Okay, so an example, I should give you an example. So also F2 acting on this one is strongly proximal. So in fact, we said before that I can push two infinite words to a joint point, but I can use a continuum of words to a joint word in the same way. So I can push somehow the whole support of a given measure to a joint point. So okay, so think about the details. Maybe okay, that's an exercise. Just nothing. And the claim G acting on X is strongly proximal if and only if for every measure nu there exists some delta X in its orbit closure. Why? Well, obviously, if I start with right, if I assume that that's the case, and I'm taking nu and mu to be in probe of X, then I know that there exists some delta X in the orbit of mu plus nu over 2, right? Mu plus nu over 2 is also a measure. So I can find some Dirac if I assume the right-hand side assumption. So by passing to subnets, we may assume that T alpha of mu converges to some mu naught, and T alpha of nu converges to some nu naught, where T alpha is the net, the taking mu plus nu over 2 delta X. Right? But from here you see that delta of X is half mu naught plus half nu naught, and delta of X is extreme point in the convex space of a probability measure. So if it is extreme point, it means that mu naught and nu naught must be delta of X, but delta of X is extreme. Is extreme in the extreme points of probe of X. So mu naught is equal to nu naught, which is equal to delta X. Good, so they converge to the same measure. Conversely, it should be easier, I think. So take delta, I don't know, choose some delta Y and mu, and so choose some delta Y. So for all mu in probe X, there is a T alpha in G such that limit of T alpha delta Y is equal to limit T alpha of mu. But we said that the Dirac measures are closed under the action. They are G invariant. So this guy has to be some delta X. So we are done. Okay. So questions about this? Okay, so I'm going to use this definition from now on. When I speak about strong proximality, I will use this. Good. So claim, of course, this is where I wanted to go. The action on the Amana boundary is strongly proximal. And in the proof, I will need so you know the Klein-Millman theorem. What is the Klein-Millman theorem? So maybe reminder. Klein-Millman is to say that. So okay, the reminder is about Klein-Millman. Klein-Millman plus half converse. I will explain. So Klein-Millman says that whenever you have that the extreme point of a compact convex set K is equal to some set T, then in fact K is the convexal, closed convexal of this set T. So if K is compact and convex. The half converse of Klein-Millman is the following theorem that says that whenever K is the closed convexal of a set T, then the extreme point of K are contained in the closure of T. So you see why it is half converse. We don't have full equality, only one containment. And I will use it. I mean, it's classical functional analysis. I'm not going to prove it. So proof of the claim. Let nu be a probability measure on the Amana boundary. We will show that we need to show that there exists, but in fact we will show that for every x, well, we knew from before it will be for every x because of minimality. So if you think about it, minimality plus strong proximality exactly implies that for every x, I can find the Dirac measure in the orbit closure of nu, of any measure. So fix some x in the Amana boundary. First, claim inside a claim, subclaim. Delta x is in the closure of the convexal of G nu. Why? If not, so proof of subclaim. If not, then by the Hahn-Banach separation theorem, we can find an f continuous function. Well, now think about it as a continuous linear functional, but it's a continuous linear functional over the functionals in the Weak-Star topology. So it is exactly a function here and an epsilon greater than 0 such that G nu of f plus epsilon is less than or equal to delta x of f for every G in G. I can separate this part and right, and delta x. Thus, the norm of f, which is equal by the lemma is not written here, but I remind you, we showed that the Poisson map is isometric. So if the Poisson map is isometric, the Poisson map is just, I mean, the norm of it is just the supremum of all. And again, why do I write G? Usually I said that I will write T, right? So let's go back to T to try to be consistent. So T nu of F it's a measure, so I don't need absolute value. This is less than or equal to by what we just said, delta of x of f minus epsilon, which is less than or equal to the norm of f minus epsilon. But that's a contradiction. Contradiction. Okay, so this shows the subclaim. Now, how do we prove the claim from the subclaim? This is just the half converse of Kreil-Milman. So look, we now know, I just don't want to move to the next page before we understand what we need to do. We already know that every delta x is here. So all the x's, all the Diracs will be in the convex hull of this place. But if all the Diracs are there, then by taking a convex combination, it means that this space is everything. It is all prob of g of x. I mean, if I have the extreme point of the, let's say by the usual Kreil-Milman, this is just the probability of all the probabilities over the Amana boundary. But now I will say I will use the half converse of Kreil-Milman to say that the extreme point of K contains in the closure of T will be this guy, G nu. So the extreme points will be contained in the closure of G nu. And this is exactly what I wanted to show. Okay, I will write it, so don't worry. I just wanted to explain it before. So, we saw for every x, delta x is in maybe let me write it like this. We saw that delta x, x in x, is in the convex hull of G nu. By usual Kreil-Milman, the convex hull of the left-hand side is there, which is everything. But this is equal to the extreme of delta x, x in x. So the convex hull. What did I want to say? So this is equal to the okay, no, this is not that's fine, sorry. By half Kreil-Milman inverse, we know that the extreme points of this set is contained in G nu closure, but this is exactly delta x, x in x. Good. Okay, and we are done. So what do we know so far about the Amana boundary? We know it's minimal, it's strongly proximal. We know also that it is trivial if and only if the group is amenable. We also know that all of the stabilizers are amenable. But I want to show something. So I want to show now that it is a universal minimal and strongly proximal space. So any other minimal and strongly proximal space will be a G-equivalent image of the Amana boundary. So before showing this, let me state the following lemma that I will use. Lemma: if G acting on M is minimal, and the action of G on X is minimal plus strongly proximal, then any GUCP map from C of X to C of M is an injective star homomorphism. I mean, is a star monomorphism. Is a star monomorphism. And there is at most one such map. So in fact, okay, I mean, this is something we just need to observe. It's not a lemma, it's observation. So let's observe it together, okay? So suppose I have a map phi that is GUCP from C of X to C of M. Then I can consider the dual map phi star that goes from the dual to the dual. So from the dual of C of M to the dual of C of X, but I can restrict it to the unit ball of the positive elements, namely to the probabilities. So this is just, it will take me from prob M to prob of X, right? This map phi star. And but also in prob M I can embed M as the Dirac measures. So I want you now to consider this map. Phi star restricted to M. So so I'm saying since X is minimal and strongly proximal, for every M in M, there exists, and for every X in X, the delta X will be in the orbit of phi star of M. Again, let's read this. Phi star of M is of a little m is just a measure in prob X. So this is just some kind of nu. This nu must have, because of strong proximality, some delta. Because of minimality, it must have every delta in its orbit closure. But so what? Okay, so what do I want to say? So delta X is the limit of some net T alpha phi star of M, which is phi star of limit T alpha of M, which is phi star of something, some mx. Here we just set mx to be this limit. Aha, so m is minimal. M is minimal. So m is also equal to gmx. And phi star maps this to g delta x, which is x, right? So phi star takes m to x. So now if you go back, it means that phi was in fact a star homomorphism. Right, so it maps mx onto delta x. And you know, whenever I have a map between two compact Hausdorff spaces, the pre-dual map, not the pre-dual, the pre-composition, right? This map to this map is pre-composition. So pre-composition with this must be a star homomorphism. So phi is star homomorphism. But this map was onto, of course. So phi is injective. What about the uniqueness part? Well, if psi is another such a map, repeat the process with phi plus psi over 2. So if you do it, then we get an mx. So this will show us that. So this will lead some mx, some new mx for this map, and half phi mx plus half psi mx will be equal to delta of x from this construction. Therefore, phi star of mx will be delta of x, which will be psi star of x. So both phi star and psi star will do the same. So phi and psi will do the same. Okay?
Guy,
Yes.
can you repeat why phi is star homomorphism?
Yes, because it maps. So phi, I'm not saying that phi star is homomorphism. I'm saying that phi is star homomorphism. Okay? I'm just saying if this map, how do you move from this map to this map, right? This is just the dual map. I'm just saying this comes from by precomposition, if you think about it.
Yeah, you just restrict, right? You restrict the. No, you don't restrict anything.
No. Here I restrict. I'm saying something very general. I'm saying whenever you start with a GOCP map, and you realize that in fact you take okay, so you can think of it if you want as the extreme points of this into the extreme point of that. So you map the Gelfand spectrum of this to the Gelfand spectrum of that, then it means that you have to be star homomorphism. So okay, so let me say this. If it is not clear to you, then verify why it works, just by writing the compositions. Okay?
Okay.
It is just to compose the maps and to say that, right? Because you already know that how such map arises. So okay, so theorem. If x is minimal plus strongly proximal, there is G equivalent map from the Amana boundary onto x, namely, we say that dh of G is necessarily it's unique, the universal minimal plus strongly proximal G space. So we're now about to show that the Amana boundary is in fact the universal minimal and strongly proximal G space in the following sense. Whenever you have another minimal and strongly proximal G space, then it is an image, a G equivalent image of the Amana boundary. So maybe just a remark, the existence of a universal minimal plus strongly proximal G space is originally due to Furstenberg, and it's also called the Furstenberg boundary, not to be confused with the Furstenberg-Poisson boundary. Furstenberg boundary, and denoted DFG. And to prove the original existence of the space is really easy. So let me just say, I'm not going to do it because we're using other tool, so why should I bother? But let me just briefly describe it to you. How do you do it? I mean, in general, if you just want to prove that there exists such a universal minimal strongly proximal G space, you can take all minimal strongly proximal G spaces in the world, take their product. Now you have a huge space. Now it's not hard to show that every proximal space has a unique minimal subspace. So take the unique minimal subspace of this huge strongly proximal space, show that this guy has to be the universal minimal and strongly proximal G space in the world. So just proving that there exists such a space is an easy exercise. Quite easy, yeah. But we showed you something else. We showed you that we get it naturally as a category in a categorical manner somehow, right? Okay, so let me prove it, the theorem. So proof.
Is the set of isomorphism classes always a set? Like
up to something.
Set...
I don't know, up to something.
Right.
No, you mean when
up to G. Yeah, when you say take all.
When I say take all product, of course, I mean up to identifying the same.
But is that a set?
I think yes. Yeah. Okay. I'm not going to get into it. Let's leave it for later. But yes, I think that's a set. I think. The thing is like this, Alon. If your group has a cardinality kappa, then you cannot act
right.
something too big.
Absolutely. Okay, yeah. My mistake. Thank you.
No, it's not a mistake. It's a good comment.
Yeah.
Okay.
My trivial comment.
No, it's not trivial. Okay. So fix. I mean, I just don't want to go into this direction. So fix. So I'm going to prove it. So fix x0 in x. This x is just minimal and strongly proximal space. Okay. And consider the map that from G into X. So X is minimal, so it is Gx naught. That maps G to Gx naught by the universal property of the Stone-Check compactification by the universal property of the Stone-Check compactification this extends to a map from beta G into X, right? So, okay, what if maybe I said too many words to say something very simple. Let's say it in a simple way. Here you take, right, in the Stone-Check compactification, G is dense. So elements here looks like limit of some T alpha, right? T alpha in G. So this should go to limit of T alpha X naught, okay? Something like this, okay? So that's the, so this gives us, okay, so this is continuous, okay? This extends to a continuous map. And this is onto, of course, because Gx is minimal. So now I have, in the dual way, I have an embedding, a star monomorphism of this guy inside C of beta G, which is L infinity of G. But I also have our good old friend phi that takes us to the G injective envelope. This is the GCP projection. Right? But now use the previous lemma to say that this whole map is a star monomorphism. By the previous lemma, this whole map, this whole map. Yes, and I should have said that this is a G equivalent map. So this will be G star monomorphism. Yes. So this GUCP map that goes from C of X to C of D of HG is a G star monomorphism. Therefore, there exists a map that goes like this. Good? Is this okay?
Is the Stoncheck compactification is not necessarily minimal, right? The
No,
G action on
it is not minimal. It is just point transitive. So,
right.
So E, the trivial element in G, is orbit closure. Well, naturally, it is the closure of G itself. So it's all beta G. So
Again, sorry.
Beta G is equal to G closure, which is equal to
Right.
G E closure.
Yes, it's transitive, but it's not necessarily minimal.
No, it's not minimal. No, the corona is invariant. I mean, beta G minus G is invariant and closed and compact.
Mm-hmm.
I did not use the minimality of this space at any point.
Right.
Because it's not.
But it's still the universal transitive flow.
Yes, it is the universal point transitive G flow. That's right. Okay. Do you have questions? Please interrupt me or ask me if you do. Let me give you an exercise. I don't know, maybe I will put it in the exercise sheet. In the third one, show that if G is non-amenable, then DHG has no isolated points. Also, a last thing we can say about the Amana boundary, I should have mentioned it in the beginning, but maybe another claim: the Amana boundary is extremely disconnected. I remind you, it means that the closure of any open set is open again. In particular, it is totally disconnected. And it follows from things we mentioned last time, because it is also injective. So, okay. So now I would like to start. So now I'm going to leave it to rest for an hour or so. Okay, now we have only 15 minutes, but I mean also at the beginning of next meeting. And I want to discuss about some very important construction we have in C-star algebra. So, listen.
Guy,
yes.
can I ask first about this last thing that you said?
Yes.
You said the Amana boundary is extremely disconnected.
Yes.
But this Amana boundary is supposed to be the Fürstenberg boundary, right?
Right.
Which should be the Gromov boundary, for example. For
no. No, Fürstenberg does not mean here Poisson-Fürstenberg, or Fürstenberg-Poisson. It's not the same Fürstenberg. I mean, okay, it's the same person, but it's not the same boundary. Fürstenberg-Poisson, which you describe as the Gromov one, well, Gromov is one of the models of this guy, is a boundary that comes with a so if you have a measure on G, you can assign to it a boundary that is called the Fürstenberg-Poisson boundary. It is not our Fürstenberg boundary that is completely topological and has nothing to do with measures. Okay.
Mm-hmm.
And also, just let me, if you mention this, okay, I will not go in this direction, but let me mention, if you know something about your Furstenberg boundary, the Furstenberg-Poisson boundary, so you probably know that, right, this is nothing but the harmonic function, the bounded harmonic functions on G that are bounded. So I can put it inside L infinity of G, right? And I can take, so, and then usually you show that how this becomes a sister algebra. Usually you construct a GOCP projection here, which is just taking convolution with mu with itself infinitely many times, and then say that you have a fixed point somewhere because everything is compact. So a limit point. So this gives you a conditional expectation or a GOCP projection, which gives you a Choy-Force product on this guy. This makes it into a sister algebra that with the Gelfand spectrum, you can call it the Furstenberg-Poisson boundary. The thing is that this also shows that this guy is G-injective. So in particular, this guy is also extremely disconnected. So your question does make sense also in this area, I mean, but that's fine because Gromov boundary for hyperbolic groups is just a model for the dynamics. So you can identify this as L infinity of pi mu and some measure. This is the Zimmer model for the Poisson boundary. But you can also, if the group happens to be hyperbolic, then it is also isomorphic to L infinity of the Gromov boundary with respect to another measure. Fine. This is just as standard, just as Lebesgue spaces, or just as probability spaces, not topologically. Because topologically, this will be extremely disconnected, and this will be metrizable. Okay, and not extremely disconnected in particular. Okay, so okay, this was just to answer your question. I mean, I'm not going in this direction. Maybe I should erase this, because if somebody will try to read these notes, then they won't understand the connection. Okay.
Guy, previously we showed that if G is amenable, then the Amana boundary is just 1 point, right?
Right.
And now you say that if it's not amenable, then it's like every point is a part of an interval, or
something like that.
And does it have like, can it be, do we have examples where it's connected and examples where it's not connected, or it's?
So it's always extremely disconnected by the next claim, which is in particular totally disconnected. Right, these are weird spaces. These spaces are never metrizable unless they are finite.
Ah, okay.
Okay, these are weird spaces in some sense, topologically speaking. Okay, so I do want to start the construction that is called the cross product, and I wanted to begin with some philosophy. So philosophy, you know, if you like actions of groups on topological spaces, then you have a problem. Why? Because the action of the group on the topological space is not a topological space. It is an action. It is a different creature, right? So it takes you out of your category somehow, and now you can look on the category of actions. Now you will tell me, but Guy, wait, if I have, I know, sister algebra, which is a G sister algebra, there is an action of it. Again, this action is not a sister algebra. It is an action on a sister algebra. And then I come and say, no, it's also a sister algebra. Or more precisely, I can construct a sister algebra, not in a natural way that will encode the action. So, and to stay in the category. And even in the commutative case, I will get something that is non-commutative. So the construction I'm going to show now, even if I will start with a commutative action, namely of an action on a topological space, I will get a non-commutative topological space that will encode this action. Non-commutative topological space, namely a G-sister algebra, a sister algebra. Okay, it also will be G-sister algebra, but okay. And so, okay, and just to give you a hint of what we're going to do, so the idea of cross products of sister algebra by group action, it goes back to von Neumann, and the idea is like this: given a G-sister algebra, given a G-sister algebra A, the goal is to construct a single sister algebra, single as unmarried, single as a one sister algebra that encodes A, G, and the action. The procedure is going to be very similar to what in group theory called a semi-direct product. Okay, so it will be very, very, if you know what semi-direct product is in groups, so it will be very close to it, very similar. We will create a sister algebra that I will denote like this, with the property that G will sit there as unitaries in the sister algebra, as the unitaries of the sister algebra, and there will be a natural inclusion A in it, and it will be minimal in the sense that it will be generated by A and G, by their copies inside the product. And the most important thing is the following one: it will be a G-sister algebra, and the action on elements, right? A sits inside, and A will be G invariant because it will encode the action. But the action on A under this construction will be inner. I remind you that G is going to sit as unitaries. So the action is going to be inner. It's going to be conjugation by these unitaries, i.e. the action becomes inner. Okay, so that's what we're going to do. Now let's do it. Now the most important part is to understand what we want to do. If you understand what we want to do, you will see that you will understand the construction somehow. Okay? So I'm going to start with the construction. Let A be a unital G-sister algebra, and let's C subscript C for compact G A be the set of all functions from G to A that are finitely supported. So this, by the way, generalizes also to non-discrete groups, but I'm not going to do it. I'm going to do it under the discrete sense. We'll also write elements of the tzitz here as A, T, T, T and G, A, T and A, with AT is equal to 0 for all but finitely many T. Okay? And now I need to define the product and the star operation. I want to make it a star algebra. So let's turn it into a star algebra. So I'm going to define F star. So let me first write the definition and then explain it, okay? So let's write F to be sum of ATT and G to be sum of BTT. Again, it's finitely supported, so all of the ATs and BTs are 0 with the exception of finitely many of them. I'm going to define F star to be T inverse acting on A star T, T inverse, and F times G is going to be TS in G, AS, S times BT, ST. What do I do here? Why did I define it like this? So let's explain this. Explanation. I claim that this is the only way I could define it if I wanted the action to be inner. I remind you that in the previous page, I wrote here that I want to have this property. I want to have the action to be inner. And I claim that there is only one way to do it so that the action will be inner. And this is the way I define it. Why? So explanation. So I'm claiming this was the only possible way to make the action inner. Why? Because suppose you want to multiply ASS with BTT. Now, both the AS and the group elements need to sit there as operators. So when I will multiply this, it should look like S and T and G, AS, S, BTT, but they should sit also as operators. So I can also erase it's associative. So now, if they are operators, then of course I can and if I did succeed to make the group elements to sit there unitarily, then I can multiply it by S star S, right? So suppose now I'm doing a reverse engineering. I'm just saying, suppose I did manage to construct this as I wanted, then I'm allowed to add here, to write this here, all right? And there is no problem. But as I said before, I did this in a way that made the action inner. So this guy is in fact equal if the action is inner. So this was true if G sits inside as unitaries. And this is true if G acts as we wanted. So what do I want to write? ST in G, A, S times BT, ST. But this guy is already an honest to Guy element in CC of GA. So that's the reason I define it like this. What's the reason I define this? Well, think about it. If you want, so you probably, if you want G to sit as unitaries, then you want T star to be T inverse, right? I mean, verify this. I mean, it's easy. It's the same idea. So that's the only way I can do it somehow. Okay. So this makes it into a star algebra. It's easy to verify. And just a remark, a note. Let me extend this place a little bit. Note, when A is equal to C, and I want you to keep in mind this option always. It's a very interesting option. If A is equal to C and G acts on C trivially, then CC of GA is nothing but what is sometimes called the group ring. Right? It's just the space of all alpha TT. Alpha T in C to all but finitely many. T. So now the question is, how to complete CC GA to make it a C-star algebra. Right? And I need to complete it somehow. I do have a star algebra. Now I need to give it a norm and to complete it with respect to this norm. And there's not going to be a unique answer to this question. We're going to have two options. One, universal, in a universal way. And the other one we'll call the reduced way. So we'll have two kinds of cross product, a universal or a full cross product, and a reduced cross product. And we're over time, and I don't think I will be managed to, yeah, so maybe I will keep the completions to next time, but this will be the point where I'm going to start next time. So next time, I will describe the universal cross product and the reduced cross product, and I'm going to show you a lot of properties of these guys. So they have a lot of good properties. They encode the action. You have the possibility to understand properties of the actions from properties of the C-star algebras, and also the case where the C-star algebra A is just the field of complex numbers is going to be very interesting. We're going to get in these cases what is called the reduced group C-star algebra and the full group C-star algebra. Okay, so we're going to continue from this point next time. So stay safe and see you all next week in Zoom, of course.
Thank you, Guy.
Bye.
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 ביי יונתן, ביי מיכאל, ביי כולם, ביי ארי, ביי אלון, ביי בני.
גיא, אני יכול לשאול אותך
Of course, בטח.
על מה שאמרת קודם.
כן, כן.
על הפואסון באונדרי.
כן, בטח.
אפשר אולי לעצור את ההקלטה?
כן, I'm stopping the recording.
סבבה.